Hello and welcome to this math video. In this video, we'll attempt to integrate the Dirichlet function over the interval 0, 1. Here's the definition of this function, and it's famous for not being differentiable. We'll go through the process of trying to integrate it using Riemann integration, that is, using the subs and ints of sets in a partition of the integral. But the difficulty is that numbers can't be represented exactly. So how are we going to represent these numbers in a computer program? Well, we'll soon find out. So we're going to partition the integral over equally sized sets over the interval 0, 1. This will be done by choosing a prime number as our fraction and dividing the interval into this prime number of equal intervals. We'll use a prime number so it doesn't exclude numbers like a half or a third as our rational numbers, because we won't include the rational numbers that are on the boundaries of these intervals. So we'll use the prime number 19 to start with, being close to 20, and being both large and small enough to illustrate our interval when we try to integrate it, so as to watch and understand what is happening. We'll use Riemann integration so that we'll calculate the upper and lower sums, finding the largest and smallest value of our function in each interval in the partition. Then we'll use computer code to track down rational and irrational numbers to go into our intervals. We'll use a program to search for all of the rational numbers and give them an order like this, so that the fractions with a small denominator come before fractions with a larger denominator, so a half is ahead of a fifth, and this way we'll get all of the rationals in each of the intervals that we want. We'll similarly search out irrational numbers to put into each interval. We'll search out these irrational numbers, sums of multiples of integer square roots, and added to an integer. We'll get all of these sorts of numbers to get into each interval. And these can have an ordering too, so that an irrational number made up of the sum of one integer and one square root is simpler than one made up of the sums of lots of square roots. So the simpler number comes first. So now we're in a position to find all of these numbers and put all of them into the intervals. Now to create a data type to store these numbers. This data type will have these attributes. Firstly, we can describe this number using a string. This will be its name that describes how it is created. This number is 3/4, so is made by dividing 3 by 4. And we'll calculate its corresponding value as a decimal number, so that we can sort it later against all sorts of other numbers. And we'll give this number a type, and it's a rational number, so type is set to 1. We could have numbers with as many types as could be named, like algebraic and transcendental, for example. We'll just stick with 2 types for now. And now to determine which interval it's in. We'll say that it's in the 5th partition, which means that it's between 5/19 and 6/19. I've nearly called it a rectangle because they look like rectangles in a graph of a function, and especially in this function. And so now to describe a real number that is irrational, we'll write down its string or name that describes how we got it. It's -1 plus the square root of 2. I've put the integer here first because I want to write these numbers down in order, and I'd like to write the integer first. And I've calculated and stored its value as a decimal, which is fairly messy for irrational numbers. I've done this so that I can sort it against other real numbers. Its type is 0, meaning that it's an irrational number. I won't have to do any complicated coding to work out that it's irrational. I'll just put it in here, so that it's easily remembered later on in the program. And I'll store the partition that it's in here. So now to start writing our first function, which will store a large amount of rational numbers in an array, which stores these numbers as real numbers, with these 4 attributes. We'll firstly set these global variables from the function arguments. The GL stands for global, so we'll store the global variable n of intervals, which is the number of equal partitions, which we agreed would be 19, and the total number of rational numbers to be found, which is n of reals. This number may be found to be different when we finish the function. This array called interval stores the number of rationals found in each partition and is an accumulated total, so each element must be initially set to be 0. So now we'll set all of our indexing variables. I will be used to store each real number found, and in this function we'll be finding rational numbers. P is the number of intervals in the partition that have enough rational numbers in them, and the function will stop when P is equal to the number of intervals. A and B represent the rational number between 0 and 1, and will be able to represent any of these rational numbers. K is a sort of variable to stop the main loop from getting into an infinite cycle. And so we'll start the main loop, which will stop when either enough rationals have been found or when all of the intervals have enough rationals in them. I've also included this variable, which prevents this loop from cycling infinitely. I used it during the construction process, but I like to keep it here if I wish to modify this function later. I can set its maximum value in the loop to be even larger, like 10,000. So we'll only include the fraction AB if these two numbers are coprime, because if they aren't, then they could stand for another fraction that we've already found, like 2/4 is equal to a half. Then we'll evaluate this fraction's decimal value. We'll calculate the interval that it's in. If this interval isn't full yet, that is, it has less than 6 entries, then we'll start storing this number. We'll start by storing its decimal value, and then we'll store its name or string value. Then we'll store the type of number it is, that is, as a rational. And if there are more than a certain amount of rationals in this interval, then we'll increment the amount of intervals that have enough rational numbers in them. We'll also increment the number of rationals found in this interval. And we'll store the location of this interval in this number's interval attribute. We'll increment this index variable to make this function able to store the next real number. Now to get the next rational or fraction, we'll firstly increment the numerator. And when the numerator is equal to the denominator, we have to increment the denominator and set the numerator back to 1. But we want to miss out on all the rationals that are on the border with the intervals, so we'll increment the denominator again when it reaches this value. The total number of rationals would have changed by this function because it tries to have a good spread of rational numbers over the entire interval. I'll just include this coprime function here for completeness. I won't go into too much detail. It uses Euclid's algorithm to find the greatest common divisor, so as to determine whether or not two numbers are coprime. So we need to have a function to print out this list of rational numbers, so that we can see that the function that gets all of the rational numbers is working properly. We'll firstly load in these global variables. Then we'll create a loop to go through all of the rational numbers that we've inserted into the list. Then we'll print them out using this write command, which is popular in JavaScript. This function prints out the number of rational numbers found in each interval or rectangle. It uses a loop to go through the entire list of intervals. And here's some of the rational numbers that we've found, with a string describing how they were found, a decimal approximation, whether they are rational, 1 means that they are rational and 0 irrational, and the interval that they've been found in. There's also the printed output of the number of rational numbers that we've found in each interval. Now to make a function to sort the rationals in order of size. We'll firstly declare the function and internal variables, and load in the number of rationals found. We'll use the selection sort algorithm to find the location of the rational number with the minimum value so we can put it in the front of the list as we move through the list. Then we'll use this classic swapping algorithm on each of the 4 attributes. So here's this list of sorted rationals. They are in order of size and are grouped together in their intervals, so it will be a lot faster to find a rational number in any given interval. So now to get the irrational numbers. They aren't as nice as the rationals. We can get a long list of evenly spaced rationals that are between 0 and 1 that we can't do for irrationals. So we have to go through lots of irrationals that run the risk of being unevenly spread in this interval. So here's a list of numbers that we'll use the square root of. None of these numbers have the square of an integer as a factor, otherwise they'd only be an integer again, or a repeat of one of these square roots. And we'll get the square roots of these integers and put these into another list of numbers. We'll select a range and number of square roots. The range selected here is 3, so the coefficients of the square roots will range from -3 to 3. The number of square roots is 4, so we'll only use the first 4 numbers from this list. So this is the list of square root values that we'll be using. And this is an example of a coefficient list. The numbers can vary from -3 to 3. We'll get the irrational number by multiplying each coefficient by its corresponding square root value and adding them together. This should give a unique irrational number, and its string value should be this when we simplify it. Then we'll evaluate its approximate numerical value and place it into the value internal variable. Now we'll find the leading integer, that is, the integer that when added to all of these square roots will return a number between 0 and 1. We'll get this using the floor function. So this is what the leading integer is for this sum of square roots. We'll put this value of the sum of square roots and the leading integer into this value attribute. And so this is what these numbers are. And so this is what the value of this third expression is. We'll append the leading integer onto the beginning of this string to give this string the exact value that this number is equal to. To get the next irrational number, we'll increment this coefficient list by adding 1 to the first number on this list. And this is the next number after that. When we get to the largest number in the range, then we'll set it equal to the minimum value in the range, and increment the next value in the list, like a counter. And if we have a list with only zeros, then we'd increment this list to a 1, followed by a lot of zeros, because we'd need at least one square root in the list to make this number irrational. Now to look at the corresponding function for finding irrational numbers in these intervals. We'll look for sums of square roots of integers that we've described just now. We'll now set these internal variables and one global variable. N of reals is made equal to the number of rational numbers found so far, so that these two lists will be nearly equal to each other in size. N of intervals is the number of intervals in the partition, which is 19 in this case, like before, because we're using the same partitions. N of square roots is the number of square roots that we're using, like the square root of 2, the square root of 3, etc. We'll set the global variable to be equal to this value. We'll set the number of irrational numbers found in each interval to be 0 initially, because these will be calculated as totals using a loop. We'll make a loop to go through all of the square roots that we'll be using. Then we'll get the ith integer on this list. We'll get the square root of it and pass it onto its corresponding decimal value. We'll set the coefficient corresponding to this square root to be minus range, because that will be the initial value that we'll start with. We'll set these indexing variables that perform the same functions as in rationals list. I is the ith real number found, P is the number of intervals filled, and K is a special variable used to stop the while loop cycling infinitely. So we'll make up this while loop the same way as we did for rationals list. The loop terminates when both enough irrational numbers have been found and when all of the intervals have enough irrational numbers in them. It will also terminate if too many cycles have been made. We'll store the name of this function in this variable, which is short for string. We'll add more to this string as we cycle through the next while loop. And the decimal value of this irrational number will be equal to 0 to start with, before we start to add irrational numbers to it. We'll make a loop to go through all of the square roots that we wish to add to it. So this is where we add the square root value onto the value of this irrational number. If the integer coefficient of this square root is positive, then we'll add it onto the string in this way. And if it's negative, we'll write a minus sign followed by a positive integer coefficient. Now we'll get the leading integer of this expression using the floor function. We'll add this leading integer to this expression to get the correct value, which is between 0 and 1. We'll also append this leading integer onto the front of the string. This number ix is the interval that this irrational number lies in, and is calculated in exactly the same way as for rational numbers, by multiplying this number, which is between 0 and 1, by the number of intervals, which is 19 in this case. And if there aren't too many irrational numbers in this interval, then we'll include it. Each interval must not have more than 6 irrational numbers. We'll copy all of the information into this real number data type, and especially mark it as irrational. And if this interval has more than 4 irrational numbers in it, then we'll mark it off as having enough, and so increment p, which is the number of intervals having enough irrational numbers in them variable. When this number is equal to the number of intervals, then we are able to escape the main loop. We'll then increment the number of irrationals in this interval variable. We'll also store the interval that this irrational number is located in inside this real variable. So now that we've found and loaded in this variable, we'll then increment this index variable to store the next irrational number. Now to increment the list of coefficients that we'll use to determine the next irrational number. This index variable j is the index variable to the coefficients of the square roots. This Boolean variable tells the next loop whether to increment the next number in the coefficients list. This gives us the number of coefficients of the square root that are equal to 0. They can't all be equal to 0, otherwise the number won't be irrational. So we'll start this loop to increment the coefficient list so as to find the next irrational number. We'll get the value of this coefficient somewhere in the list, that is the square root of 2 or 3 or 5 or so on. We'll increment this value. If its value is too big, like 4 or 5, we'll have to give it the lowest value and increment the coefficient of the next square root. We'll set this coefficient to be the lowest value at minus range, which could be minus 4 or minus 5. If the coefficient value isn't too high, then we'll escape this loop. We'll insert this new value into the list of coefficients. We'll increment this index variable to point to the next coefficient in this list, since we're going to increment the next coefficient in this list. We'll go through the list of coefficients of square roots again to see how many of them are 0. We'll check that there isn't an integer not having any irrational square roots added to it. If there is, then we'll increment the coefficient of the square root of 2. It doesn't matter if it's incremented outside the main incrementing loop, because it will only be a 1 multiplied by the square root of 2, and 0s multiplied by the square root of 3 and 5, etc., and it wouldn't get incremented again by the main incrementing loop. I've inserted this code here to jump out of the main loop early, so that the same irrational numbers are not found all over again, due to the coefficients vector overflowing and counting all over again from the beginning. I won't go too deeply into this part of the code, because it is more for error correction rather than for doing math. And then we'll save the number of irrational numbers found into this global variable here. So this is the function that prints out all of the irrational numbers that we've found. It's almost identical to the function that prints out all of the rationals, only the irrationals are stored in variable b. So this is a list of the unsorted irrational numbers that we've found so far, with their name, approximate value, and what type of number they are, rational or irrational. The interval that they've been found in is also included. This is the function that sorts all of the irrationals, which is almost identical to the function that sorts rationals. It sorts them according to their decimal value. This is the list of irrational numbers after they've been sorted by the size of their approximate decimal value. Now to copy these two lists of rational and irrational numbers to one long list of real numbers. We can do this without having sorted either list first, because they'll be sorted again anyway. We'll start copying the rational numbers onto this list. We'll copy in the global number of rational numbers that we've found. So we'll copy this list of rationals into the list of reals. And we'll set the global number of reals equal to the global number of rationals, so that we can join the irrational list of numbers onto the end of this list, if we want to do it this way. Then, after we've found the list of irrational numbers, we'll call the function to copy the list of irrational numbers onto the end of the list of the real numbers that we've found so far. So we'll load in the number of irrationals, which will be equal to the number of irrationals that we've found, and we'll set this second indexing variable to be I plus the number of rationals, so that we'll append this list of irrationals onto the list of rationals. We'll copy all of the irrational numbers onto the end of the reals list, after all of the rational numbers that we've found. So then we'll export the total number of real numbers that we've found to its global variable. So this is the function that will print out all of the real numbers that we've found, being the rationals and irrationals mixed together. It is very similar to the other two printing functions. Here is the function to sort all of the reals, which is similar to the other two sorting functions. We can just load the two unsorted lists into this real list and sort them all in the sort reals function, so we'd only have to sort them once. This is a sample list of sorted reals with rational and irrational numbers mixed together, but in order of size. This is a plot of all the points on the number line. We can see here that there are rational and irrational points in each of the intervals, so that the infimums will all equal 0 and the supremums will all equal 1. Now to have a closer look at these functions sup and inf, which we'll need for Riemann integration. The sup or supremum is the least upper bound of a set, and is the element with the maximum value in a finite set. The inf or infimum is the opposite of sup, being the minimum valued element in a set if it is finite. In infinite sets, the values of sup and inf need not be in the set. The Dirichlet function has only two values, so the value of sup can only be 1 as its maximum, and the value of inf can only be 0 in this range of values. Here's a plot of the Dirichlet function. Since we know if a given number is rational or irrational, we can tell what the function will return. In this plot, we have rational and irrational numbers in each interval, so we can safely say that the infs and sups of each interval will be 0 and 1 respectively. Now to make the function to actually integrate the Dirichlet function, we'll load in the number of intervals, which will be 19 in this case. J will be the real number indexing variable, which will point us to the next number on the number line. We'll create a loop to look at every interval in the partition. Sup is the supremum of each interval and is initially set to 0. We'll cycle through each point until we find the next point in the interval that we're looking for. This is made easier by the fact that all of the numbers are in order, so we can count from where we left off last time. And if this number is rational and in the interval, then the sup of the interval is 1, and we'll set each upper sum equal to 1 if they are found. And we can increment j here until it's in the next interval. So we've already found the first number in the next interval before we've cycled through the main for loop. We'll do a similar thing for the irrational numbers. We'll reset the indexing variable to all the real numbers to be 0. We'll make a loop to go through every interval in the partition. This time we'll calculate the lower sums. We'll set inf equal to 1 this time until we find an irrational and then set it to 0. We'll go through all the real numbers until we find the first irrational number in the list. We'll then check that this irrational number is in the interval, and we'll check that it's irrational. I like to build these redundancies into my programs. If this number is irrational and in the interval, then the inf of this interval will be set to 0. Then we can look for the next real number in the next partition. We can get the upper and lower sums by adding all of the values in the intervals, so we must initially set these to be 0. We'll make a loop to add up every sup and inf in the intervals. We'll actually add them up here. Then we'll divide this number by the number of intervals, so as to give us the upper and lower sums. This is because the width of each interval is 1 divided by the number of intervals. So now to print out the results of our efforts. We'll print out the sups of each of our intervals. Then we'll print out all of the infs of our intervals. Then we'll print out both the total upper and lower sums of these intervals. Then this program will decide whether or not this function has been integrated successfully or not. If the upper and lower sums were unequal, then the function has not been successfully integrated. So this is how we'll tie all of these functions together so as to integrate the Dirichlet function. And these are the results. All of the sups are 1 and all of the infs are 0, and the upper sum is 1 and the lower sum is 0. So it wasn't successfully integrated, but we managed to do it using a computer. So we got this far using a computer to find the upper and lower sums. So the program is successful in showing that the function couldn't be integrated. So I hope that you have found this video enlightening, interesting and exciting. Please click like and subscribe if you did. Please feel free to share this video and to leave some helpful comments. And thanks a lot for watching.